right? Okay, so it gives me great pleasure to introduce Dan Klein, who recently got a PhD from Stanford, and he's a co-author of many famous papers with his advisor Chris Manning, and he's now at UC California at Berkeley. And he's going to talk to us about unsupervised learning for natural language processing. And as a reward, I'm giving him one of our caps.
Should I wear the cap?
It will improve your talk.
I don't think it will improve my hair, though. Is it for me?
Yes.
All right. Just to start you guys out, I thought this was going to be a 90-minute talk. So it's either going to be really fast or really truncated. It's kind of up to you guys which. And please ask questions, but be aware that if you ask too many questions, you'll get half the talk. All right, so let's back up a little bit and not lose sight of the dream here. The dream is we would like our machines to process our email, do translation. Whatever it is you're hoping for those robots to do for you, it probably involves communicating with them and talking. And you know, there's some issues here. Do you always want to be talking to your machine? Do you want to be in an office full of people talking to their machines? Maybe not, but you'd like the capability. But we can't do this yet, and people in this room all pretty much know why that is. Language is complex, it's ambiguous, and that's why we all have jobs. So solutions to these kinds of problems, we need a lot of linguistics, we need a lot of machine learning, and we're all hard at work at that. The problem is, for many practical purposes, I'm still stuck trying to enter information into my cell phone by pressing buttons over and over again until I get the letter I want. So there's kind of a gap between what we're trying to do and what Star Wars promised us quite a while ago. In terms of how we're approaching solving these problems in NLP today, just kind of only looking at a small time horizon here and looking at statistical approaches and learning approaches, there's really two paradigms. And again, everybody's pretty much familiar with both of these. One is supervised learning, which I think of as looking something like this, where essentially the model is one of instruction. You show a bunch of examples of how some kind of transduction or mapping should be performed, and statistical learning theory takes over and learns to essentially memorize that and relate new examples to previously seen examples. And the second paradigm that I'd like to push a little bit today is unsupervised learning, which looks something a little bit like this, where essentially information comes in and the paradigm is less of pattern memorization and more of pattern detection, where the signal comes in, you have inputs, but you don't necessarily have any transduction specified. Instead, you learn a transduction on the basis of some kind of statistical pattern detection method. Okay? So any questions to here? We're going to be talking mainly about this today, and the basic outline is although I've skimped on motivation here, I'm going to talk about a couple different cases where you can think about doing unsupervised learning in more and more structured environments, and the kinds of things that you have to do in order to make unsupervised learning work reasonably well. So I'll first talk about some simple toy examples with just point pattern clustering, and then I'll talk about some experiments with unsupervised information extraction, and then I'll finish with some experiments in unsupervised learning of grammatical structure of various kinds. And again, encouraged to ask questions whenever here. Basically, if we only get to here, that's one talk. If we only get to here, that's another talk. And if we get all the way through, then that's a marathon. Okay? So let's first start with point patterns. This is a game that really has nothing to do with natural language. And I mean, in some sense, it doesn't have anything to do with anything, but it's good for illustrating the issues. Basically, in point pattern clustering, what you want to do is, and I'm only talking about 2 dimensions here today, you take some patterns of points and you want to put them into groups. So that's your task. And there are lots of methods. There's a lot of clustering methods. If you take a clustering course, you're going to learn about all kinds of things, some of which I'll talk about today and some of which I won't, like k-means clustering, complete link clustering. There's a bunch of algorithms, and each one takes your points and magically produces some partition that may or may not have any bearing on either the right answer or the answer you were looking for or whatever you were hoping was going to happen. But the important point is different clustering methods give you different results, and you want to know what kinds of clustering methods, what kind of models are going to discover the patterns that you were looking for and under what conditions. So instead of it just essentially being that you have a huge list of algorithms and then a huge list of results and you just try them all and do some kind of inspection, you'd like to understand in some way what the interplay between the analysis method and the output is going to be. So here's an example, k-means, which probably everybody's familiar with. but you can get the PowerPoint animation anyway. The way k-means works is you start with points. They're shown here in black. And we can kind of look at just the black points and think, oh, there's two clusters, right? There's that cluster and this cluster. We start with means, which are here, the plus and the x. And what happens is the means just go somewhere. And some of the points are closest to the blue mean, and some of them are closest to the red means. Then we do an assignment of points to their closest mean, and we re-estimate the means. So we then say the means are now the average of the points that have been assigned to them. This can be viewed as an expectation maximization algorithm. I'm not going to say too much about it, but then when the means move, that induces a new separation on a new clustering on the space. We do this iteratively until it converges, or there's a million variants of k-means. So this essentially is a model is essentially a density model. It says, I have these points here, and I'm going to explain why I have the points where I have them by putting these Gaussians on the space. So my points are here, my means are there, and my hypothesis here is that my data is a sample from these two Gaussians, and the whole clustering process is telling you where those Gaussians go. So that's essentially my hypothesis. The model form is then a mixture model where you have a mixture of these k components. Each one is specified by a mean here, which is a center. That's specified per cluster. And then sigma, which is just some kind of scale parameter that I haven't said anything interesting about here. You can set it to what you like. This doesn't always work, not surprisingly. So if I give this, any guesses what's going to happen? If I give this pattern of points? So you might want red and blue. You're probably going to get something like this. And that's because, OK, I might be able to see a pattern. But in this particular model family, the best way to account for the variance in the data is by using the Gaussians lengthwise. How about something like this, where you have a big dense cluster and a really light cluster? Right? I might look at this and say, well, here's one cluster and here's a second cluster. What's going to happen here? Really test your k-means knowledge. That's exactly right. What you're going to have is the best way to account for this data is essentially to use your means up here where there's a lot of data and call those outliers. It's the best thing you can do for likelihood. So this, in some sense, these are failure cases, but they're failure cases that if you think about them, they kind of make sense. They're what you'd expect given the model family you chose. So then comes the question, what happens when I get some data that looks like this, where there's essentially two patterns in the data? All right, this will be a kind of an allegory for later when we actually have language data here. There's always multiple patterns in your data, and I say put that in two clusters. And if I said that to a human, the right response from the human is, well, what clusters do you want, right? There's not really a unique answer, and probably probably your clustering algorithm is going to detect this one if it's got some kind of spherical bias, where this is one cluster and this is another cluster, but this is another perfectly reasonable answer. And how are you going to know which one you're going to get? Let's say, for the purposes of this allegory here, we want this one. And our k-means produces that one. Okay, so that's basically the problem. There's multiple patterns in the data. I want this one, but my clustering procedures is producing the wrong one. So there's a couple options, kind of three of which I'm going to talk about, and one of which I'm just going to point to work done here. So one is if I'm naturally finding this kind of two Gaussian representation over on the left, that's because there's more variance in that direction. Well, I can change my data. I could project out the axis that is just noise for my classification. I could project it onto just this vertical axis, and then all the variation is surprise on the vertical axis, and I get the right clustering. So I could change my data. I could change my search procedure. I could say, yep, this is my data. It's in 2 dimensions. I'm using 2-dimensional Gaussians, and I'm still going to use these spherical Gaussians, but I'm going to constrain myself such that the only hypotheses I'm interested in are ones where the kind of this x-coordinate of the mean is on this vertical line. So I could just say, I'm only interested in that subspace. Well, that'll work too. It's not going to be as good a fit to the data, but inside this constrained subspace, the best way to explain the variance in the data is with the desired target. So that's another thing. I changed my search procedure. And the last thing I could do is I could change my model. So the problem was using these isotropic Gaussians. Instead of that, what I can say is so I made some really small change here, but it's kind of obvious what I've done, is now instead of looking at Gaussians that are spherical, I look at Gaussians that are elongated in this direction. It's kind of the same thing as changing my data, but essentially if I have long, skinny Gaussians, I'll want to use them this way. So I have all of these options available to me at all times, and the important thing is how do we go about looking at what our model is doing in a complex case seeing what's going wrong, and then deciding what it is we have to change in order to improve things. And a couple of these ideas are going to come up. Any questions to hear? Yes?
How did you get the first red and blue points that were close to each other? The two means?
The two means. That's a great question. I have a slide about it later. The short answer is you pick them at random and you hope you did a good job. Or you hope it didn't matter what you picked. Okay, so what to take away? You're going to have, in general, this is how I view unsupervised learning. They're kind of clustering problems. There's always going to be multiple patterns. There's always going to be multiple answers. And usually, you're not going to get the one that you wanted right off the bat. It can go wrong because you have a bad method of initialization. You can have a bad interaction between the way you're representing the data and the bias in your model because of something like the spherical bias or something else along those lines. And what often happens that I think is underappreciated is you often learn some salient pattern that's sane. It's just not what you wanted. And it's not so much a matter of, oh, this didn't work, but it worked for the wrong task. Or, I mean, you know, it could be either, but you have to look. So kind of what can you do? Well, option one is you kind of get used to disappointment, and you kind of try different clustering methods, and if none of them work, then you go label some data. And actually, that's option one if you can afford to label data and you're not interested in doing any kind of pattern discovery, option one's fine. I mean, you can see it's got fewer bullet points too. So option two, which is harder, is you look at errors. You then ask yourself, kind of in this iterative cycle, what is it my model family can and can't learn? What's it learning wrong? What do I have to do to change the data representation or the model structure in order to get it to learn what I do want it to learn, because I have some target in mind? And in that cycle is where the human knowledge comes in, right? The knowledge has to come in somewhere, because when there's multiple patterns, the system can't read your mind. And this is where it comes in, is in the engineering cycle. And there's other work here that's very good, but I am not going to say anything about except to keep alluding to it as an extra bullet point on these lists, which is Smith and Eisner from ACL 05, which is work on you can change the objective function as well. All right, so we got through here. I'm going to talk a little bit about some experiments in actually using language data and trying to get unsupervised learning working for some structured problems, in particular an information extraction task, and then I'll go on to grammar. All right, so let's say you're apartment hunting in the Bay Area. And you want to do this on Craigslist because, among other things, it's free and there's really fast turnaround time. People post things all the time. And the postings look something like this. And I didn't even look at this one. I just took a screenshot last night. See, this posting's good because it has Gardener included. It's not the kind of thing that it's obvious whether you're looking for or not. So you've got these unstructured postings, and you'd like to do some kind of search like, I want a gardener, or I would like this many bedrooms, as opposed to this many bathrooms. It may actually matter to you whether the thing you have 4 of is kind of bedrooms or bathrooms. And you can't do this because the listings are unstructured. We'd like to structure them automatically. Now, it's possible we'll be able to get somebody to label up a bunch of these apartment offers and say, okay, well, here's the number of bedrooms, here's the number of bathrooms, here's whether or not pets are allowed. Okay, that will work for apartment listings. But then think about all the things people sell on eBay. Right? I mean, is somebody going to label up every kind of Beanie Baby and what its attributes are and whether or not it was manufactured with the thing stapled to the left ear or the right ear? God only knows what's going on with the Beanie Baby listings, but there's some structure and nobody's going to label it. We'd still like to do some kind of information extraction on these things. Okay? So if we look at these classified ads, what's the structure look like? Well, here's 3 ads. They all mention something about the size of the unit that's being rented. They all say something about how you contact the seller if you're interested. And that can be in various ways. Sometimes it's phone numbers. Sometimes it's please call us at. Sometimes there's email. There's terms of kind of what's included in the lease. There's information about the location. And there's kind of features that's kind of a more generic field. Now, this is something we've made up. I'm telling you that I think this is a reasonable annotation scheme. You may have a completely different target annotation scheme. So if this were a labeled task, you'd label it differently. You wouldn't label your data like this. But basically, you can look at these classified ads like this. We'd like to learn something like this in an unsupervised fashion. So I'm going to give you a bunch of these classified listings, and you're going to do this kind of segment classify and segment task. Yes.
So there's still potentially maybe one more step you'd like is to get from 2 BDRMS to 2 bedrooms.
Oh, absolutely. So there are issues of normalization. There's issues of what we're talking about here is essentially just a labeled segmentation. This is not a complete semantic extraction. There's no normalization going on here. You might want to do all of those things if you were actually thinking of getting this into an end-to-end search that could, that's absolutely right. Any other questions? Okay, even without normalizing BDRMS to bedrooms, this is already a kind of hard task. We would have some idea how to do this if we had labeled data. How are we going to do this with unlabeled data? So first of all, the domain of what I'm going to talk about, I like to think of information extraction as being divided into two kinds of information extraction. What most people mean most of the time when they say information extraction is this nugget extraction on the left, where you have some document, almost all of it you could care less about, and every now and then there's some little nugget that you want to extract. So you have a huge document and you only want to take out, if it were these listings, you only want the price, and the rest of it you really could care less about. And in this case, most things are background, and this might actually be a really adversarial case for unsupervised learning, because how's the system supposed to know which little nugget you actually care about? But what might be a little more promising for an unsupervised method is something like a field segmentation task, like what I've just argued, where all the documents have a small number of fields. They all have these fields, or at least most of them have most of the fields. The fields cover the whole document, and you could hope that means that the structure is going to be a little more evident statistically. So we're only going to talk about this. People have done a lot of work. Obviously, I can't even attempt to recap all the work on information extraction. I can't really even recap all the work on field segmentation, but people have looked at these kinds of things. So oftentimes it's been parsing something about paper headers or paper citations where there's some small number of fields and you want to know the author and the journal and so on. And there's also things that you can broadly think of as field segmentation, either being kind of generous or abusive, depending on whether the author would agree with this characterization. But I'm not going to go into the detail of the work, but I'm happy to talk about related work if people have questions. What I'm going to show you experiments on now are two corpora. One is a classified ads corpus, which is a bunch of Craigslist listings that we took and we downloaded 8,000 of these and took 302 of these and annotated them with 12 fields. Now, we annotated them with what we thought the fields are. You may not agree, right? So that right there, you may not agree with this annotation, but it's some annotation that we think is reasonable, things like size and rent and contact information. And these listings are fairly long. There's also big bibliographic citation data that's available. It's described in McCallum et al. 99. And what we used here is it's 500 citations from 500 academic papers. They're all unique. And they're all annotated with the kind of 13 fields you'd expect, like author and title and journal number. And these are much shorter. There's kind of 35 tokens and a smaller number of fields. Right, so just to get started, where's a baseline? The baseline, I'm going to show you mainly numbers at the beginning from the classified ads task. What's the baseline? The baseline is you say everything's a feature. That turns out to be the biggest class. So you say everything's a feature, and you get about 46% accuracy because okay, all right. So I'm playing fast and loose because I know I have 90 minutes to cover here. I apologize. So how do you evaluate a method like this? Well, if this were a supervised information extraction, one thing you could do, right? This already could cause some debate. One thing you could do is you could take your whole text and you could look at each word and assign each word to a field. And then you could look at how many words you got right. So kind of a per position accuracy. That's not always what people do in information extraction. Often they look at the entire chunk and do something like F1 on the chunks, whether you got the chunk you were looking for. But since this is more of a segmentation task, the way we're going to evaluate it is to look at at a per position level, how many positions were assigned to the correct class. Now, what does this mean in an unsupervised setting? Well, we're going to cheat a little bit, but we're going to cheat in a bounded way that I'm going to explain and be willing to defend. And what we're going to do is, in an unsupervised setting, the system's going to come and it's going to put a label at each position. The labels aren't going to be they're not going to be fields like number of bedrooms or contact. They're going to be fields like 73. And it'll just assign some number. And then we're going to do post hoc a mapping between the symbols that our system comes up with and the gold fields. Now, you could say that's cheating, right? Why don't I just go to each position and give it a unique field, and then the post hoc mapping makes it so that I got everything perfect? Well, that would be cheating, but what we're going to do is we're always going to say that the number of latent states in our model, the number of labels that we can assign, is going to be equal to the number of gold fields. So we can cheat, but we can't cheat much. So you kind of figure there's a 2% here that you can disbelieve in these numbers. So what this is this is just labeling everything with the same state, saying everybody's in field 1. Well, what's field 1? Well, field 1 is under this post hoc assignment. Field 1 is going to be whichever field accounts for the most tokens in the document. And it turns out there's one field that people tend to blather on about all the features of their apartment because that's the basis on which you rent it. And that's 46% of the positions, and so that's our baseline. Okay. It's not very good, but it's our baseline. Any other questions on this? This is actually very important. If you don't believe the evaluation or you don't understand the evaluation, please do ask.
Well, just a comment that this evaluation problem is similar to what some people in speech have been doing with something called speaker diarization. So you record a whole conversation, that's a meeting of 5 people.
Okay.
And then the task is to chop it up and say, the same person spoke here, there, and there. Another person spoke here, here, and here. And there again, the system doesn't know who the people are.
Okay.
So the assignment of the system's label 1, 2, 3, 4, 5 to the actual speakers is done post hoc in a most beneficial sort of way.
Okay.
Yeah, the only catch there is the system doesn't know how many speakers there are.
Okay, here the system, I mean, you could think it does or doesn't know the number of labels. If you were really going to use this and you wanted the best results, what you probably do, if there are 9 fields, what you're probably going to do is run it with 35 labels and then do the post hoc and get a little bit of mileage from your cheating and spend an hour with a human trying to collapse these down. But just as a way of doing any kind of automatic exploration, we're going to always fix it to be exactly the number of states as the number of gold fields. Any other questions or comments? Okay, great. So what I'm going to do for the rest is I'm going to describe some models for doing this information extraction task and try to motivate how this kind of iterative design can get you to unsupervised models that work reasonably well. Okay, so one thing you could do, what's the simplest thing you could possibly imagine doing that could possibly work for this task in an unsupervised fashion? Well, you might think it's not actually that hard to segment these fields, right? Just chop them up on commas and periods, come up with some heuristic that you can come up with in under a minute. So you segment in some crude way, and then you have a bunch of little chunks that say things like, no cats allowed, and then you cluster those using some document clustering technique that I won't talk about. So now you have these clusters, no cats allowed, no dogs allowed, and then you assign them to a label in this post hoc way. And then you kind of reconstruct them back into the documents. That's a labeling. It's kind of, you do segmentation, then you do clustering, and you do them independently. It's kind of a reasonable thing to do, and it's a reasonable first stab. And it works better than the baseline. So you get 62% right there. So if you do crude segmentation and EM clustering, you get some value. We can do better, and you'd think that we should be able to do better because the segmentation and the clustering really aren't independent tasks. We really like to learn to do them integrally. So we'd like to do better. Here's our baseline. Here's segment and cluster, which is kind of our strong baseline. All right.
Don't go forward.
Well, no, I won't go forward.
Yeah. So there's a key step that you're not emphasizing, namely everything depends crucially on your notion of similarity. Right? If it has something to do with what you want, you're okay. If you're not, you're dead.
Notion of similarity where?
So if you said cluster them,
Yes. Oh, sure.
these are strings, and I have 2 of them, and how similar or different are they?
That's right. So I can explain.
In other words, how much word knowledge are you going to let me use in designing this similarity measure?
Since it's my baseline, I'm going to encourage you to not think about it anymore and then ask me the question with the actual models I'm going to present where it's very explicit where the word knowledge is. So in practice, just to give you a very compressed answer, in practice the way these were done was by doing clustering with naive Bayes, just a kind of multinomial mixture model, which means what's the word knowledge? The word knowledge is that there are words, right? I mean, and that they're kind of independent according to this particular model. Now, what I'm going to do with the structured models is I'm going to start refining that. And a lot of the refinements we make in terms of being a little smarter about how we assume these words came to be probabilistically, we could port back, not all of them, but some of them could be ported back to here and would give improved results here.
Right. So what I'm saying is that's where the unsupervised description starts to break down because it's less and less unsupervised.
I think a distinction should be drawn between knowledge-free, which is essentially, kind of you take something off the shelf, you point it at your data, and you kind of don't think at all. Unsupervised, which means I don't have any labeled examples of X, Y input-output pairs, which is another extreme. So another extreme is when I actually have labeled data. And in between, in the unsupervised methods, what you're calling supervision is really bias, right? It's how does knowledge come in? And knowledge will come in because I'm going to spend, I have more of my talk, so knowledge has to come in somewhere, right? So something has to actually get done. And what happens is I'm going to be saying, well, we want the model to do this kind of thing, so we're going to change the model in this way. Well, why do we change it in that way instead of some way that would make it even worse? Well, because I knew what my target was. So there is a process there, but it is, and in some sense, it's a worse process than in the labeled case because it's being done by a human engineer, which is, we talk about experts back in kind of this rule-based days of AI and NLP, experts being expensive. Well, people capable of designing probabilistic models are even more expensive. So in some sense, this is an expensive way to get knowledge in, but I'm going to try to argue that we're not doing anything, I'm not hardwiring anything about apartment listings, basically. And you'll have to kind of reserve judgment about whether or not the kinds of bias I'm putting in are the kinds of things that are worth the time, or whether you would have been better off having labeled some data. That's going to be up to you. Yes?
Are you also going to have some sort of a baseline where you are using essentially some person who knowledge engineer a set of very simple rules, let's say 5 minutes time. So I segment by comma, and then I say if I see some string of number, I think it's a contact. And that's sort of very simple.
Halfway. Right, so this is segment and cluster. Segment was done in that way. The segmentation was done using entirely knowledge of somebody who looked at the data. The clustering, no knowledge, and I'm not going to show it. You could imagine it, and it could kick butt. Who knows? So I'm not going to say it won't.
What I meant is instead of clustering, if I just said, well, so would that be better or worse? Because if you're
I don't know.
Knowledge anyway, then the question is.
Yeah, so there's this question of, is this the most efficient way of getting knowledge? Now, my agenda is, I could care less about apartment listings. What I want to know is, I want to know what the interaction is between the probabilistic structure of a model and the kinds of patterns it does and doesn't learn. So if you have a better way of doing this problem, I mean, assuming I get to it at all, when I talk about grammar induction, well, we've got the Penn tree bank. There are much easier ways to get the parsing numbers I'm going to show. But I don't think you necessarily learn things that I'm interested in learning through that process. So I'm not going to say that even our best results, I'm not even going to say that our supervised results, when I show you some supervised results here as an upper bound, are better than what a human could do with some clever rules. I don't know, because I haven't done the experiments. I suspect you could do reasonably well, but not that well. I mean, I show you 3 examples and they look like they're not that messy, but they're pretty bad, the data. Any other questions? Yes?
Yeah, so when you did this, you know how many clusters you want to end up with because you know how many fields you're interested in labeling, but then how do you assign the labels to each of the clusters?
Okay. I thought you were going to ask a hard question, but yes, an easy question. The easy question is, assuming I know how many clusters I have, the way I assign the labels in an automatic evaluation is I just do whatever gives me the best score. I look at a cluster and I just do post-hoc assignment. And as long as I don't have too many clusters, that's not cheating. In practice, I would have to actually have a human look at this thing and say, oh, that's the bedrooms field or something.
So you do use a pigeonhole principle, meaning if I have labels 1 and 2, and the best assignment to both would have been contact.
That's a great question, and it depends on whether you comment one line in or out of our code. And I don't know, but I think we did not use that. I think I think we didn't do that. Any other questions?
That's across the whole. You pick the best one across every exam.
That's right. Yeah, that's exactly right. So it's kind of the minimal amount of cheating that you could do. I tried to be kind of honest. So. Any other questions before I get to slides where you can't assail my integrity anymore? All right. So let's say we want to go about this job of doing segmentation and clustering integrally, where we want to have a model of this sequence that includes some hidden information at each state. Well, hidden Markov models have been around forever. They're a probabilistic model that, as you guys all know, is parameterized by these 2 conditional multinomial distributions. One that relates to how states transition to states, the transitions, and the other that relates to what words are associated with each state, the emission models. So this is a model family, and it's a perfectly reasonable model family to think that I would use for this task. And the reason for that is essentially if I labeled some data and then I trained a hidden Markov model in a supervised fashion, it would do okay. Now you could look at this and say 74%, and how good is that? Well, this is a 9-way task, and You know, this is, on the amount of data we had, this is what you get. If you have more data, you do better. So the one thing I'd like to kind of get you to imagine is imagine, for the purpose of this slide, that if instead of training on 300 documents to get this number, I trained on 8,000 documents, you know, this number would probably be in the 80s or 90s, but again, who knows. So a hidden Markov model is a reasonable model family for this problem, because if I trained it in a supervised fashion, I would do reasonably well. All right, so there may be better model families, but I'm going to claim that. So let's say we take our hidden Markov models and we train them in an unsupervised fashion. Well, what does that mean? Well, it means EM. Anytime somebody says in the words in an unsupervised fashion, they pretty much mean EM. And we know how to do that. We've known how to do that for a long time. So we do Baum-Welch to train the HMM. We fix the number of states to be the number of fields. We do kind of uniform initialization on the transitions, a little bit of noise on the emissions, and we let this thing chug and we let it fit the data, and it comes up with some point in the space of the hidden Markov model parameter space that is a local optimizer of the likelihood of our data. Okay, how does this work? Any guesses? Crash and burn, right? So this is segment and cluster. If you just train up an HMM in an unsupervised fashion, you do kind of dramatically worse. Now, part of that is because the segmentation is actually kind of smart here. So you could think this is being a little bit abusive. And this is slightly above that baseline of just saying everything's in field 1. But it's like 1.5% above, and it's nothing to write home about. And we're still far short of what you could do in a supervised fashion. And now this is where I think the interesting part of the talk is so we did badly, and this is the point where you have a choice. You could just say, let's label some data and let's not go this route, or we could say this number is really, really low, and the most interesting question is, why is it low, and how do we go about figuring out why it's low and making it bigger? All right, so what went wrong? Well, one way to kind of diagnose what went wrong is to look at the transition structure we learned. We'll look at emissions later. So here are the transition structures we learned for classified ads. There's kind of states, and darker dots indicate high transition probability. And here's the same thing for bibliographic citations. So you look at these and, is this good? Well, who knows? What's the target structure look like? So the target structure looks like this. We're kind of completely off target here. So in the target structure, what we get in general that whatever state you're in, you're going to stay in that state for the next time slice. That's actually not surprising, right? These are long states of the same thing. You have features like contact information. You have 5 of them in a row. So of course, the kind of utilities field is gonna self-loop with high probability. You get the same thing in citations. We haven't learned anything like that. You can see some hints of some diagonal structure. We haven't learned anything like that. But that's not necessarily a surprise. Maybe that's one of the important points I'd like to make here. This isn't a surprise that you would learn something like this, because this is just text data. Text data has all kinds of patterns going on. One of them is part of speech, right? Text data has parts of speech. What do parts of speech do? They jump around kind of crazy. Every word is a different part of speech from the previous word. It's kind of a rapidly mixing, rapidly transitioning Markov process. And there are so many processes so many linguistic and otherwise processes on text that you could describe using a hidden Markov model. What's to make you think you're going to learn that one rather than this one? I'm not claiming we learned part of speech. We actually learned some garbage. But imagine we were learning part of speech. It would still look wrong for our task. And it would look wrong because we essentially we didn't point our model in the right direction. So I like to think of things schematically, something like this. This is a likelihood surface. They don't really look like this, but I guess this is the best you can do in 2 dimensions. So this you can think of every point here is a hidden Markov model, and the height of the graph here is data likelihood. So there's some point in this space that's kind of the field model I'm looking for. It's possible it's a global optimum. It's possible it's a local optimum. It's possible it's neither, right? We just know that because I can train something in a supervised fashion and do okay, there's some point in here that's reasonable performance for my task. There's all kinds of other things going on. There's a part of speech model in there somewhere because I could have trained a hidden Markov model for part of speech tagging and it would work kind of okay. There's probably some model that represents some kind of discourse structure, and of course, almost everything is garbage. Like, don't forget that. I don't want to tell you this is just a sea of linguistic structure and no garbage. There's kind of garbage everywhere you turn, and a couple nuggets of good things. So we didn't learn what we wanted. How do people affect what they learn? Well, one way is by kind of doing some kind of smart initialization. If I start here and I hill climb, I'll get some garbage, but if I started here, I'd get some parts of speech, and maybe if I start kind of over here, I'll get the field structure I want. So one way you can kind of prime these things is by how you initialize. It's perfectly valid. And another way you can do it, which is what I'm going to talk about in a second, is by constraining the model class. So this is the equivalent of taking that vertical slice on the k-means example. So imagine that on this surface, we only were allowed to search hidden Markov models on this red line, which is some subspace of the hidden Markov models. Well, you know, if everything were as beautiful as this diagram, we'd be great, because on this slice, even though this thing is kind of this yucky mixture of all of these bumps, on this subset, on this subspace, things are relatively well behaved, and the maximum, even though this may not be even a local maximum in the full space, this maximum is our field model, and everything's done. Okay, so if it were just this picture, it'd be really nice. But we can essentially get mileage out of exactly that picture and exactly that kind of constraint. So I look at my task and I say, what did I do wrong? I wanted to learn diagonal, a kind of a diagonal slow mixing, often self-looping transition. Well, I can do that, right? I'm in complete control of my model. Rather than having a transition matrix that's parameterized by a whole big matrix of variables, okay, I mean, kind of the simplest thing that could work here is I say there's some scale parameter sigma, and I self-loop with that probability, and then uniform otherwise. So I'm telling you what my transition matrix is. It's with some single parameter sigma, I self-loop, otherwise uniform transitions, and then I can retrain using EM. I've restricted my model class to some subspace, and what happens? Well, so I mean, this kind of works right out of the gate. So already we've gone from something that is basically just throwing everything into one field. It's not that it actually throws everything into one field, it's that, I think this is the pigeonhole question, the best post hoc assignment is to throw everything into the largest field. Because essentially it's learning noise, and then as soon as you basically point it into the right kind of, the right subspace of hidden Markov models, you do reasonably well. So what's interesting here is I have this one parameter I can fiddle now, right? I have sigma. It says something about the scale of the structure I'm looking for. And as I change sigma, I'm going to learn, you know, I run EM, and there's still some non-determinism involved, but I run EM and I get some result. These are averaged over, I think, 10 runs. That's not true. These are averaged over 50 runs. As I change sigma, you can see kind of an interesting thing in the accuracy for these classified ads. The accuracy kind of tanks. It's down at this baseline level when sigma is too low, right? Essentially, when sigma is too low, it's just a uniform transition matrix, and
the thing that will hold it to the I don't know how many categories is the probability of W given S, right?
yes.
And it will learn which words are characteristic of which thing.
Yes, that's right. That's right.
Tell it anything.
That's right. The transition's worse than before. I mean, when sigma's down here, it's telling it.
Except that it stays in the same.
Well, it does here.
It says cluster words.
Yes. Yeah. What it says you have this process that's sticky. It's kind of sticky word clustering, but the segmentation is done integrally in that, right? It is better than a segment and cluster. Okay, so you know maybe this is just obvious and I shouldn't belabor it, but as the scale of the problem kind of increases, you suddenly start getting enough self-loop probability that you can get a hold on your clusters, and you get reasonable, you know, more than baseline numbers here. The peak is up here at about 0.9. That basically corresponds to the length of these fields, right? It's saying the fields are about yay length, and you know, that's what you want it to be. Down here for citations, it's again very abrupt, that if your self-loop probability is so low that you don't prefer self-looping, you learn garbage, but then as soon as you prefer self-looping, you learn something reasonable. And in this task, the fields are in fact quite short. Okay, so it's still not great. It's still at something like 70%, and we want to do better. We can look at our emission models too. So here's the emission models from a couple of these states, the most common words emitted from those states. And well, this is actually kind of reasonable, right? Deposit, pets, rent, and the other one's large living kitchen. Right? It's not crazy, but you know, I could point at things that I don't like about it. Like a lot of these emissions are wasting a lot of time modeling common words. Now that may not be bad. If the common words are the same in all of the states, who cares that it's modeling them? It's only bad to the extent that there's variance in the common words that is being kind of accounted for using the wrong mechanism in my model. So which I can show that happens here by making the change I'm going to describe and then showing that it improves things. So what I can do is I can say, well, I see a lot of common words in these emissions. What if I kind of used a hierarchical Bayes estimator instead and said that the way I'm going to get words here from my state is with some probability I emit a word that is common to all states using some shared hierarchical emission model here. And then with the rest of my probability, I'm going to emit a word that's local to the state. Okay, this is just linear interpolation. I said hierarchical Bayes at some point, but this is just linear interpolation, except that I am also going to learn this. Right? That's not just going to be the average distribution. Okay, so I can do this, and let's say I'm chugging along in state 5, emitting these words. Now I also have the option of either emitting them from the distribution associated with state 5, or I can emit them from the common distribution, and for different words I'm going to choose a different level in the hierarchy based on whatever, this is done automatically based on whatever makes the data likelihood best. And then you get things like this, which are much more interpretable. Right? That's not necessarily a win if you care. You may not care about interpretability, but certainly these things are more interpretable. Right? They're these kind of clean lists of words that really do kind of make sense and are thematic. And you'll see that there are still words that are kind of function words that show up, like at shows up in state 5. But at really is characteristic of locations, because that's how people describe these locations. All right, does it help? Well, 1%. But it makes things interpretable. What helps a lot more is the following. You look at errors and you say, what's my model doing wrong now? Well, this gets to the comment that essentially this is just kind of clustering words in Windows, and there's not really any model of segmentation. You do things like this all the time. Right? We know about schools and parks. They go in the purple state. We know water goes in the utility state. But this word paid, well, it kind of gets taken along for the ride because we don't know anything about the word paid. What we really want is we really want to have some kind of model of boundaries, because in our data, the boundaries are very salient, but we're not representing them in our model. So we change our model in a very minor way, where essentially, instead of just chugging along in a state and then transitioning to another state, there's a rule that says, with high probability, and we can learn that probability, that when you go from one model to another, you pass through a dedicated boundary state, and then the model, when the model is like that, it's going to learn what's characteristic of that boundary state. There is not a self loop on the boundary. There is, but it's not associated with sigma. Yeah. Okay, and this helps, again, another boost. And so I could kind of talk a lot more about what errors are left. But basically, to summarize, you get kind of the baseline model, and a naive HMM induction doesn't work much better than baseline. But if you kind of go through this process of looking at what am I learning, what is it about my model family that's allowing me to kind of lock on to these patterns? And the big one here is the diagonal bias. I'm locking on to fast-moving patterns. I don't want that. I constrain my model family. I change my estimator. I enrich my model, whatever it's going to take. And in each of these cases, that gave a kind of an incremental increase. And now we're getting to the point where we're doing about as well as the supervised system. But remember, the supervised system here isn't trained on on much data. Same thing with bibliographic citations. We actually do a little bit worse here. And the big reason we do worse is because the field lengths are much more variable in length. Okay, any questions on this?
The amount of data. So you have the same amount of data in the unsupervised case as you do in the supervised case, or are you throwing more data at it?
For these numbers, it's the same. You can throw more data at it. You do get increases. And in fact, you can beat this number. But it's so unfair to show that, because if you had that much more labeled data, that'll be like 180%. But yeah, yes.
I mean, what if you went and pulled...
These things plateau. I mean, it is true.
So it would be nice to know where the plateaus occur.
This is an important point, and I've given enough talks about unsupervised learning of various kinds to know that I should say this very clearly. Models which are able to learn the right structure are usually straitjacketed in some way. So you do something like this diagonal bias that says, no, I want this pattern, and then EM does the right thing. Basically, EM will always do the right thing if you give it no choice. And by the time you've straitjacketed that much, often what you find is your model capacity is so diminished that you do plateau. You get a bunch more data, but you aren't actually capable of using those parameters. So an open question is, how do you go about building models? Is it some kind of incremental learning? How do you go about building models that have the capacity to exploit large amounts of data in the way a supervised method would, but don't get distracted by their own capacity? Right? There's this trade-off that when the capacity gets small enough to learn the right thing, well, the capacity is small, and you plateau. Any other questions here? Let me see how we're doing on time. All right. We could pretend these are just the talk conclusions. We could just stop here. So basically, field segmentation problems are the kinds of things you could imagine showing up in other contexts. But the important lesson here is naive EM fails to learn the target structure. But there are kind of these processes we can go through about looking at what's being learned and adjusting our model or our data representation, our estimators, and kind of we can really do all three in order to improve things. And so far in this part of the talk, I would say that the takeaway message is that EM will do the right thing if it has no choice. And that sounds kind of content-free and like a joke, but it's actually true. You think about your model and you think, all right, lexical probabilities are distracting this. How do I remove them from my model? Or, it's not just about kind of straight-checking your model. It's also like the boundary state here. When we added the boundary state, that was actually enriching the model, but it's enriching it in kind of a very controlled way where the pattern that we suddenly allowed the model to detect was so salient in the data that it did detect the right thing. So you always want to think about what else is in my data that I could learn incorrectly. So am I right that this talk is meant to go till 11:30?
Yeah.
Okay, so there's this big choice point. I could stop now, or I could try to do some fraction.
You took away my watch. So
I took away your watch. Well, I know what time it is. It's 11:20.
just keep going.
Keep going. All right, so I'm going to barrel on. I'm going to barrel on quickly. So we all know what parsing is. There are various kinds of parsing. I'm going to talk a little about dependency structures that look like this, and a little bit about phrase structure parsing. So here's the thought experiment. And some of you have, I think, seen part of this talk before, so you know this thought experiment. Thought experiment is, I give you a bunch of sentences like this and say, learn the dependency structure automatically. I'm going to lock you in a room with sentences. You're going to draw arrows like this that link up subjects and their or verbs and their subjects, verbs and their objects. And so what occurs to you is most likely an early thing that will occur to many of you is something that's occurred to many people, which is, let's find pairs that have high mutual information and link them up. Right? It's a good statistical test, and it's going to give me some structure. People kind of talk about this much earlier, but the two best results I could think to point to for numbers of doing this in practice are URT 98, which just does kind of greedy linkage, kind of like competitive linking, and Mark Paskin that kind of does the kind of full-blown EM with kind of a proper generative probability model. This is a really nice paper. So let me sing the praises of this paper for a little while. What Mark does is he built exactly the right generative model for this kind of structure. He trains it on 30 million words of Newswire, kind of all the Newswire he had available on a Beowulf cluster. He trained this thing for running on like 500 machines. He trained this thing for about a week and a half. Right? Massive data, massive computation. Okay. And then structures come out. They look like this. How do you evaluate them? The way we evaluate them is by taking a golden quotes, either ignore that or you know what I mean, golden quotes dependency structure, and we check to see how many of the arcs are correct. So how's that work? Well, Mark gets 39.7%, right, using this kind of beautiful model, tons of data, tons of computation. There's an easier way to get 40%. Right? If you just link things up at random, subject to a non-crossing constraint, you do better than that. Now, this is where you kind of have option one, which is kind of give up and say something's just horribly wrong with grammar induction. But the other option is, look, if you did something that was basically sensible, and you did it right, and it does worse than random, something is going on. So the most important thing here is not that it didn't work, but to figure out what happened. So what happened here? I mean, the biggest thing that happens is if you get a sentence like this, the high mutual information is going to be between the nouns. Just kind of global fact about language, the nouns and sometimes the adjectives and any numbers are going to have huge mutual information. And so you learn to link up kind of the subject and the object. Well, that's always the wrong thing to do. It's worse than random. If you're doing randomly, you'd sometimes do the right thing. Here, you're always going to do the wrong thing. And that's kind of important. That's where these terrible numbers are going to come from. Here's one from the Pentry Bank. Expect brushbacks but no beanballs. You link them up. Well, is that the right thing to do? Well, it is a little murky because we're not sure what we're doing with coordination anyway. But they've only occurred once and they occur together, so they get linked up. Doesn't matter whether there's any kind of grammatical relation. They're just syntactically correlated. There's all kinds of reasons you can be syntactically correlated other than grammar, and the biggest one is topic, and that's not what we were looking for. So here's a new year begins in New York. We'll come back to this. It's learned actually the right thing, which is new and York go together, but it's kind of indiscriminate about it. This is a different problem from these, right? This is the problem that there's a trend in my data, topical correlation, that I'm learning that I didn't want to learn. This is a valence problem. We'll come back to it. So one thing you could do is you could just do the same game of linking things up that have high mutual information, except do it with word classes instead of words. Then we wouldn't be able to learn that Congress and Bill have high mutual information. We might hope to learn things instead like verbs and prepositions have high mutual information. And you do the same model with word classes. And then you realize that Carroll and Charniak did it in 1992, although they didn't realize they did it. And they did some things that made it even worse. But you clean up their stuff a very little bit. This breaks random. So you think, well, that's good, right? So already this shows that you bleach out the information that you didn't want, you get some improvements. The problem is, if I was interested in low computation approaches, I could have just linked every word to the previous word, and well, that would have worked better. So kind of, it's nice to beat random, but really we're not really playing yet. This is still too simple a model. This is just saying link up parts of speech that commonly co-occur. This really isn't going to give you much. In particular, you get these really common, really small configurations that it crashes and burns on. So if you say stock prices fell, well, stock links to prices. Why? Because verbs do take nouns to the left, but they tend to only do it once, right? Whereas what this model is going to tend to learn is noun to the left, good, and you're going to link, you're going to link it over and over again because if you had one, you want two. So this isn't quite the right model. I don't have time to go into what the right model is, but I'm happy to answer questions. Basically, all of these models talk about probability of a head given an argument. We can just do that, and we get the kind of Paskin model from 2001. We can do it on word classes, and although we're going back in time by about 9 years, it works better. And what kind of something like the Collins supervised model, one of the big things it does integrally is it talks about things like distance. Like not only am I linking this argument into this head, sorry, I meant argument given head. Not only am I linking this argument to this head, but I have some notion of distance or valence or subcategorization that tells me what I've already done. And if you add that in, and you can add it in an extremely crude way that just conditions on the distance. And that's all that, just doing that already gets you kind of above linking up adjacent words, which is pretty much what you have to be doing in order to claim that you're playing the game. Yeah?
Are you learning the word classes here, or have you got a parts of speech thing?
The answer is more complicated. The short version is pretend I have a part of speech tagger and I'm using the gold ones. You can learn them, but when we learn them, we don't learn them integrally. But it still works. Any other questions? All right, so this is neat in one way. This is neat in that this is an example of looking at what the model did and could represent and could not represent, relating that to the errors. Right? So one error was the topical association. We simplified the model to get rid of that. Another error was this lack of, was kind of linking two nouns to the verb. We got rid of that one by enriching the model to have a notion of distance. So these are cases where you change the model and things get better. This is not impressive in that this isn't actually a good number. Right? So that's why there's lots more of the talk, although we probably won't get through all of it. But that's what I want you to take home, is not, great, we're ready to replace all of our supervised dependency parsers. I want you to take the process away. Yes?
Is distance the same as in the Collins model, sort of next to, not next to?
No, this is, you could think about this as the kind of the most simplified Collins model you could possibly. You take anything that looks like a detail and you remove it. And distance here is a Boolean variable that says, am I the first argument on that side? That's it. So this is, it's simple. It's very simple, yeah. That's why it works. Okay, so now I want to kind of talk to you about what the errors are. Oh, I didn't get to this slide in terms of cleaning up. All right, sorry. You get the non-NLP audience version of what these are. So here are the dependencies it over-proposes. And the real question you should ask yourself is, do I care? And what does this mean for this whole notion of evaluation? And you'll have to answer those yourself. One thing it does all the time and gets dinged for in that 62% is it really likes to say that the determiner is the head of a noun phrase. Probably half of you think that's a really good idea and half of you think that's a really bad idea. So make up your own mind. Another thing is, oh yes, there are theories. Yeah, and half of you like the one theory and half of you like, I don't know, how many people think this is a good thing? Let's raise your hands. How many of you think this is a bad thing? How many people don't want to answer while there's a video camera pointed at you? Okay, so think what you like. Proper nouns, it kind of, this is like, first name, last name, and it says the first name is the head. Who cares, right? A bunch of these, and then you see them over here, right? The gold dependencies say the noun should have been the head. So you see these paired errors where you make some systematic change in what you learn, and you kind of see it on both sides. You can link these up in a kind of scrambled way, but the important thing is there is a killer mistake here, something that you absolutely do not want in your model, but it's not actually up here, right? It's kind of down here. The killer mistake is, and these are kind of hard to parse, the killer mistake here is when you have a noun phrase modified by a prepositional phrase. It looks at this and says, wow, that's a lot like a verb having a subject and an object. And it makes the preposition the head of the whole thing, right? Just like the verb would have been the head of the whole the whole constellation. So basically, the preposition's the head of that whole thing. That's really not what's going on, but that's the worst thing that's left, and it's not up at the top here. All right, so you get this model. You can worry about how much you care about this white space here. Unstructured text comes in, word pairs come out, and you make a couple changes, and you can get a model that's over baseline, which is nice, right? I mean, this is something that for a long time we weren't able to do, but we can do a lot better. In particular, we can do a lot better on phrase structure parsing, and I'm tempted to fly through this and just go to a results slide. Is that good for everybody? Okay, so constituent structure is interesting. If you try it with EM, it doesn't work. It doesn't work because I said I get to this slide, but now you'll have to ask a question if you want to hear it. It doesn't work for a lot of good reasons. Oh, no, we're going back.
This is not Gestapo here, and there is no law which says you have to end at such and such a time. You're here at my pleasure.
Okay. So when I said, does flying through work for you, I should have only been looking at you, and you were shaking your head? Okay.
You talk pleases me, so why don't you...
All right. Everybody take a breath. We're going to do it again slowly. All right, I'm going to assume I've still motivated for you that context-free parsing is interesting. Probably you wouldn't have come to this room otherwise. We can do context-free parsing. The reason we think we can learn PCFGs for parsing is because if we train them off a tree bank, it basically works. Let me be clear that even though you get 77% accuracy when you just use the vanilla tree bank grammar, and we can get 90% by playing all kinds of games, first of all, those are still PCFGs. They're just complicated ones. And second of all, now we're talking performance, not whether or not this whole endeavor can work, right? We're kind of a decade back in unsupervised things. In terms of can it basically work, PCFGs are a model family that can basically represent grammatical structure. So we look at it and we say, the PCFG model family, there's one out there that kind of gives me tree bank parses. How can I go about finding something like that? Okay, well, the basic thing you do is you say what you always say, which is I'll use EM, and of course it doesn't work because it never works. You say I'm going to use EM, and we've known how to do that since Larry and Young 1990, at least, but they actually tried this on some grammars. So what you do is you say I have a grammar, it's got n symbols, they're called x1 through xn, and I'm not going to worry about what they mean until later. And I have rules, and they're all going to be in Chomsky normal form, so I have kind of all of these rewrites. Xi goes to xj, xk. I have this full binary grammar, and then you do EM on this, and so again, all of you either know exactly what that means, or I'm not going to explain it, but basically you do some kind of iterative reparsing until this converges to something. And even Larry and Young didn't think this really worked, and they were kind of writing a paper on it at the time. And why doesn't it work? Well, there's a lot of reasons, but one kind of reason why this is even worse than learning HMMs is, so for HMMs you have this sequence, and there's something hidden at each point. And you don't know what it is, but you know where it is, right? You know there's one of them per position. Whereas for trees, it's just so much worse than that. So you have a noun, a verb, and a noun, and you'd like to have some hypothesis that has kind of a subject and a verb, a sentence and a verb phrase. Well, instead, you can kind of rotate the tree, and you no longer have that node here. So even if you could have figured out what it meant if you had had it, you just don't have it anymore. Now you've got this kind of subject-verb group. You just get these other analyses, and the search operators, it's kind of really hard to get from this one to this one, is basically a big mess. And so the idea was this didn't work on toy grammars, how's it ever going to work on real grammars? All kinds of problems with that approach. One problem is somebody asked early on with k-means, how did I get this initial kind of positioning on the means? Because it seemed to work out really well. Well, in kind of in 2 dimensions, everything works out well, unless I choose like the exact wrong position for the means. But for most of these models, most of the time when you're using some kind of model, some kind of learning procedure like EM, there are symmetries to begin with. So imagine just doing k-means, way back to point pattern clustering over here. And I run k-means here, what happens? No idea? Somebody's got it. Okay. What happens is, this is a saddle point. It's an unstable equilibrium point because essentially this point, I mean, it depends actually what your algorithm does for breaking ties, but this point, which one's it closest to? Well, it's kind of closest to both, right? And you can kind of sit here happily. EM can get stuck on these saddle points. You kind of sit there, and you're never actually going to move towards the clusters because the red and the blue are being pulled in exactly the same way all the time. There's nothing to distinguish which one belongs over there and which one belongs over there. A common way of breaking that symmetry is with noise. So I inject some noise, and now the blue one is kind of marginally closer by just accident of its birth to this cluster, and it's going to end up with that cluster. There are other ways to do this, and this is, again, more of an allegory than anything else. I'll show you some concrete examples of this. The allegory is how could I have avoided random initialization? Because I don't want to just inject noise in high-dimensional spaces. One way to avoid injecting noise is to kind of associate in some way, and I'm being very vague, I'll be concrete in a little bit, in some way associate each mean with the data in some way. So one thing I could do is I could say this point is going to be red. That's my definition of red. I don't care, I'm not saying where the red cluster is or what the red cluster should be, but I'm telling you this point is red and this point is blue. That's enough to break the symmetry. Okay, so this is injecting a small amount of prior knowledge that's doing the symmetry breaking. Often we can do this structurally so that kind of the inherent meaning of the symbols is different. So what does this have to do with trees? Why didn't I talk about this earlier? Well, imagine you're doing kind of inside-outside algorithm with PCFGs, and you're doing what Larry and Young did, running EM with PCFGs. And so you've got sequences like noun, verb, adjective, noun. And there are these symbols floating over spans. And you're going to be calculating posterior probabilities in this process. And you're going to be saying things like, for this span, what's the posterior likelihood of having a constituent with label x1 or x2 according to my current model? Well, over noun and verb, what's x1, what's x2? Well, they're exactly the same to begin with. All of these symbols are completely interchangeable. And now, if I inject some noise, suddenly the symbols will mean something, but they'll kind of mean something random, and it probably will go badly. But remember, the dependency parsing kind of worked, right? I mean, we'll actually do better with phrase structure parsing, but it didn't have that problem of cataclysmic failure. And one of the reasons for that is you can think of any dependency grammar of the simple forms I've shown as a PCFG. And in that PCFG, the symbols in the PCFG aren't things like x1 and x2 that are just symbols like the means for k-means. What they are is they're symbols like the noun projection, the verb projection, right? Well, what can go over noun verb? If I talk about inside outside and I talk about the posterior probabilities, what can go over noun verb? Well, this symbol can and this symbol can, but not this one. And so the symbols are all kind of, the symmetry between them is broken by the data. It's kind of a structural symmetry breaking. And this lets you avoid injecting random noise. So when we learn these dependency models, there's no need for random noise to get you started. The model kind of breaks its own symmetry, whereas over here, when you're dealing with just straight up PCFG induction, you do have this problem with noise and needing to break symmetries. So you'd like to avoid that. Whoop.
So when we said, like, you want to assign that dot to the red mean, that dot to the blue mean, you really need this only on the first iteration.
That's right.
You don't need, in other words, you're not making a statement about the redness of that dot forever.
Like all parables, we can argue about what exactly it means. You're right. For k-means, literally, all I have to do is do that in the first iteration, and then I can relax that constraint.
For example, two dots from that cluster, call one of them red, call one of them blue. And as long as you let it go in the second iteration,
it will still work. Yes. So if you were wrong in this, you might be better just letting go. What I was trying to allude to is, down here it's actually the opposite. We don't actually specify, in the dependency case, we don't actually specify something like this bracket has this label. What we do is we kind of say, it's the opposite, it's structural. We say this symbol is kind of compatible with only these data points. And so you can think about it that way, saying it's not a statement about this point, it's a statement about this mean. Basically, this mean isn't permitted, so we can think of it as the blue mean is not permitted to be assigned to this point. It's kind of a different way of thinking about it. For k-means is really equivalent, but here is actually something different. One would look like partial supervision, or some kind of bracketed constraint, and the other one looks actually like an inherently non-symmetric model. Any other questions? Okay, so in this game of PCFG induction, we all know how to evaluate trees in general, but since we're dealing with systems that are just going to say, here's a tree, and there might be some crazy labeling about whatever the model thought it should call these, call the symbols at each node, a nice way to evaluate unsupervised parsing is to ignore the labels and just look at bracketing, unlabeled bracketing. Now, there's precision in recall, but since in practice, some systems, in practice, systems vary widely on whether or not they propose full binary trees, but the tree bank is not fully binary. One thing you can do in order to get your numbers to go from 0 to 100, which is the best justification I can give for this, is to only look at recall. Right? So what does it mean when you only look at recall? It means you always guess binary trees, and your precision numbers are worse than your recall numbers. Okay, full disclosure. But I'm only going to report recall numbers here. All right, so you want to do well at learning these trees. A lot of people have tried a lot of things, and a lot of different things. And the reason people have tried a lot of different things is because this basic thing that should work doesn't seem to, right? You would think we know we're trying to learn something like a PCFG, and we know EM fails, and so we try everything else we can think of. So Adrian's has this method that says, you know what, the reason we can learn natural language is because there are these special kinds of shallowly detectable grammars. They're not full PCFGs. They can't be because of learnability results. So we kind of come up with a subclass of PCFGs. We run our learning. We get 16% bracketing. Yeah, it's pretty grim, but it kind of looks nice on paper. Alex Clark has a method that essentially has these mutual information filters. The sentence kind of undersells it. This is cool work too. But basically, it has these filters for trying to decide what's a constituent, and then it tries to assemble them using minimum description length. There you can get about 34% recall. Remember, these are the kind of the generous numbers. These are just recall. Menno van Zanen has the kind of a linguistically appealing method where you say, okay, forget trying to learn anything probabilistic. What I'm going to do is just line up pairs of sentences that are kind of what a linguist would call minimal pair. So I line up sentences, I look at how they vary. And I say, if I have a sentence that kind of, I have two versions of the sentence that only vary in one place, that must be a constituent. And I use a kind of minimal pair heuristic to learn constituency. That's also very slightly better, 35.6%. So again, if you're into low computation approaches and you're dealing with English, you could just give everything a right bracketed analysis because right bracketing is basically the way English goes. It's English specific, admittedly, but often it's just exactly right. And here's the Van Zanen number with the alignment-based learning. Right branch is just kind of a lot better than that. And again, this is where kind of you have your two options. You can either kind of get really depressed about it, or you can try to think, what exactly is going on here that's causing us to kind of detect structure so badly? Something's got to be going on. We've got our data. We've got basically good models and reasonable tools for finding them. People are pretty hard on EM, but you know, it's a reasonable thing to do. And what are we learning? You want me to summarize the rest, I assume. Even you would think. This is just too long for somebody to listen to me talk. This is how are you guys doing? Keep going. Okay. I always assume I like to listen to me talk more than you guys do, but
well, that's still true.
Yeah. Well, after about 5 hours, we'll be seeing that. Yeah. Okay. Okay. Good enough. All right. All right. So let's say you're at this point in time, and what do you do kind of approaching this problem? You tried a whole bunch of things that haven't worked. One thing is to go back and say, well, what has ever worked for this kind of problem? And I actually think the standout thing that has worked for learning syntax is distributional clustering. So if you kind of look back in the history, you can look back kind of all the way to 1992. Distributional clustering is basically learning parts of speech. And it's working, and kind of people keep coming up with new methods of doing distributional clustering, and they keep working, right? It's kind of the statistical trends are so salient that this is something that basically works. So let's look a little bit about distributional clustering, how that relates to everything else we've been talking about, and then see how we can turn that into grammar learning. All right, so distributional clustering for learning parts of speech says, I can characterize a word by the kind of context it occurs in. Okay, already I'm being vague. We can define context in many different ways. One way of defining context is kind of the joint symbol, word to the left and word to the right. So this is a bunch of context of the word president. Here's one occurrence. Here's another occurrence. And then each word is characterized by a vector of contexts. And then we can cluster those vectors. I'm being vague again. How do you cluster? Well, every time you come up with a new one, you get a new paper, and that's why this says many others down there. There's a lot of different ways to do this, and it basically always basically works. So the two basicallys are sometimes it fails, and it's not like suddenly you can replace your supervised part of speech taggers, because you tend to get these more syntactic semantic classes that encode a little bit of the semantics because of collocational trends they detect. So it doesn't exactly work, but it kind of reliably learns decent structure. Since this is all about probabilistic clustering, a lot of these formulations here have nothing to do with probabilistic formulations. A lot of them are based on kind of some kind of low-rank matrix factorization, truncated SVD or something like that, a lot like LSA. But you can kind of do this in a probabilistic framework, but it's a little weird. So how would I give a model of a sequence that's hidden? And so here, S is the sentence, and C is going to be the word classes. And I'm going to try to do this like a sequence model. Now, you know what sequence model would be natural would be the hidden Markov model. So I'm not going to give you the whole story about how people think hidden Markov models would learn parts of speech, but then they don't. And anyway, distributional clustering is what works. So how does it look like? Well, it kind of looks like this. You go to each position, and you say, at each position, there's a word class C. It's hidden. I don't know it. But there's some marginal probability over C. And then C generates the current word according to one multinomial distribution, and then it generates the context according to another. So you can kind of think of this as a low-rank matrix factorization too in a KL norm. But so I have this probabilistic model for this point. I have the same model at the next point. So the next point is I choose a class, I generate a word, and I generate its context. And then at the next point, I generate a word and its context, and so on. So this is kind of like a sequence model. I have classes at each point. I have emissions at each point, these darker red probabilities. The thing is, instead of linking up classes to the class before it, I'm linking up classes to context. So you can kind of think of this as a broken hidden Markov model. This would be the hidden Markov model. What's broken about it is I'm generating everything 3 times, right? Not something I want to do all things equal. But the big difference between these, this is kind of the opposite of before. Before, when we were dealing with hidden Markov models and they weren't working, the problem was I wasn't staying in the same state for long enough. There's kind of, I was changing too quickly, and I needed to kind of make the connections between the states stickier. Here, if I try to learn part of speech with an HMM, part of the problem is I now have this channel through which I can kind of route information about this word. Okay, at this point, I'm predicting a word. I'm doing it on the basis of what's come before. And I can route anything I please, any kind of linguistic structure I please through that hidden channel. I'm hoping what's going to come out is I'm only routing part of speech information through it. But I can route a whole bunch of things, including the field structure of a classified ad. So what this essentially does here is it breaks those links. It says, rather than a sequence model where this decision could be made on the basis of the entire history in any way you please, it says you have to relate it to the very local context, which forces you into descriptors that look more like parts of speech. Okay, so I think this is basically a good idea that even if it's taken a while to figure out why it worked, basically works. Any questions on this? Okay, so the whole rest of the talk is essentially doing this for phrase structure. So, all right, so the question is, can we do this for phrase structure? And now you know the answer is yes. Basically, you look at spans like fell in September, and you look at their contexts, and you try to cluster them up. And you think, is that going to work? Well, you know, as far back as Zelig-Harris, the thought from the linguistics community is, you know, most people say no, right? And I skipped the whole argument about how there are arguments that you just shouldn't even try. But in principle, you might think you'd be able to do this. The problem is it kind of works in exactly the way that word clustering works, right? I'm showing lexical sequences here, but in fact, when I do these experiments, from here on out, everything else is just going to be on parts of speech. But if you do this on lexical sequences here, you get these classes like the final vote, 2 decades, most people, and that's kind of a good result. They're distributionally similar, so they go into a class. The bad result is of the is distributionally similar to with a, which is distributionally similar to without many. So the thing is, you get these clusters, but you didn't get the thing that makes syntax harder than word classes, which isn't what kind of thing is this, but does this span go in my tree or not? That's much harder. Here's some pretty pictures that say how it's much harder. So what this is this is the result of taking a bunch of known constituents of these three types, noun phrase, verb phrase, prepositional phrase. You look at the counts of the parts of speech that occur kind of bounded on the left and right. So kind of determiner noun is some point here or somewhere. I don't know which one. It's some point on here, and it's associated with some descriptor that says, I occur between beginning of sentence and verb. I occur between beginning of sentence and modal. And everybody has a vector of these, and then you look at the first two principal components of those vectors. And you can see that they're basically cohesive. Even in 2 dimensions, you've got some separation between these classes. This is just the labeling task. If I gave you the unbracketed trees, could you cluster the kinds of constituents into the right groups? Tell noun phrases from verb phrases. That's actually pretty easy, and this already gives you evidence that it will work. This is the question of, you look at all common sequences, and you say, now I'm going to try to cluster apart, and it's the exact same, first two principal components of the context vectors. What I'm asking now is, what is it that's the same between kind of a prepositional phrase and a verb phrase? That's the same between those, but that's different, on the other hand, for these kind of non-constituents, like determiner, preposition determiner. And the answer is kind of nothing, right? They're just kind of all kind of strewn together. So the really hard thing about trees is distinguishing these two classes, where one is, I'm the class of things that go in trees, and the other is, I'm the class of things that cross constituents that go in trees. They're very different tasks, and this is the important one, and it's the hard one. Okay, so we'd like a model that kind of looks like distributional clustering, because that seems to work. I'm not going to talk about this, but basically we want something that's enumerating over trees. And we kind of like a model where if there's going to be two classes, like a plus and a minus class, that they're kind of inherently different things. Here's a model. I'm going to give it to you. I'm going to report results, and then we're done. This is a model of sentences given trees. And there's something weird with it, and you see if you can notice it yourself. The way you generate a sentence, and again, these are words here, but in practice when I run these experiments, I run them on part of speech strings. The way you do it is you go to each span, and you go to each span, and for each span, just like in distributional clustering, you generate what goes in the span using just a single multinomial distribution. They get pretty sparse, right? You generate what's in the span, and then you generate the context on that span. So here you generate this big thing conditioned on plus, just the symbol that says I'm in the tree, and then you generate the context condition just on plus. And then you do the same thing for all of the other spans. So for all of the plus spans, we're generating the filler and the context independently, conditioned just on this is a constituent plus. Then we do all of the other spans as well. So we go to each span that isn't part of the tree. So for example, this is one tree. There are many trees, and we'll sum over them. For this tree, this node here is in the tree, but fell in here is not part of the tree. And so for those nodes too, we generate the filler for the span and its context, except now we do it conditioned on the other class. We do it conditioned on minus. So this is kind of, it's a two-class distributional clustering. There's only two classes, plus and minus. But there's this interesting way in which they're linked, in that for each analysis, the plus classes nest like this, and the minus classes don't. Turns out this is all you need to basically get some decent tree structure out. And the key thing is this lets you do nesting because of the constraint on these plus classes, but there's no recursion here. It's just like there's no backbone in the hidden Markov model. There's no probabilities or potentials attached to rewrite rules. This turns out to be both good and bad. It's like any of these learnability things. It's good in that it lets you learn good structure. It's bad in that you can't always represent quite as much as a supervised model could have. Also, just to brace you, these numbers, okay, so here's the right branching number again, 70%. These are short sentences that have had their punctuation removed. These are, I think these ones are actually only from 10-word sentences. That's why this is kind of an astronomically high recall for right branch. Okay, these are short sentences. They're easy. A good kind of lexicalized supervised parser would be getting these, 98%. Would do very, very well. Okay. This is not a good number, but in general, it's something that's hard to beat. This model, the CCM, the constituent context model that I just showed you, gets about 82%. So it's doing above right branch, which is significant in that it's finally detecting structure. But again, this is far below what a supervised parser would do. What does 81% mean, right? This is kind of, unless you're looking at parsing numbers on short sentences, it's kind of hard to know. What it means is usually things are right. We detect noun phrases. We detect prepositional phrases. Occasionally we screw up and do a subject-verb group instead of a verb-object group. We do it all the time. And then anything that looks like a hard ambiguity, like PP attachment, usually the result is we can tell there's a prepositional phrase. We just put it kind of in the wrong place, but kind of a place. So in general, good results for an unsupervised parser is still that we basically learn the grammar, but we're not doing great at the hard disambiguation tasks. I mean, more like we're doing terribly at them. There's a spectrum of errors. You get things like it puts the system so far, it puts kind of modals and infinitives together into a group. Any analysis you can think of, some linguist has argued for. This has been argued for, but I think most people would say it's probably wrong. We do kind of in-between things like possessives. We put the possessive particle with the object here instead of with the subject. Which one you prefer? There are theories, right? And then we bracket inside noun phrases. I mean, this is just clearly the right thing to do, but as anybody who spent time with a tree bank knows, it was a policy decision to not do that. So you get dinged for all of these, although this one you'll only see on a precision number. Okay, so what happens when you put these guys together? I won't say anything about how you do it, but you kind of do it in the simplest possible way. The dependency accuracy doesn't actually go up very much. I don't know how much to trust these numbers, right? It's too easy to do something completely different that's still reasonable in dependency, and the goal dependencies aren't always right in the first place. In particular, we have no idea what we're doing with coordination, but it gets a little better. Be happy about that if you like. You can get a substantial improvement from adding the dependency model we talked about before to the constituent model on constituency. So I think that's actually the evidence that this is an important combination, not anything up here, but the fact that when you put them together, you start doing much better on the constituency. If I train a supervised PCFG on these sentences, so this is the naive supervised PCFG that is just the kind of blind rewrites, just a tree bank grammar, no lexicalization, no binarization, no smoothing, only trained on these sentences. So this is not, this is not state of the art, but that's actually only getting about 92.8. So
actually, this is on the test data, or
here there's no distinction. Here this is a 90-10 split of this data. Yeah, you could worry. These aren't. They're on the same bit.
I understand the first thing because it's not supervised, so
yes.
There is no distinction because it learns it and all that. So what's the 92.8?
This is you take the.
Is it tenfold internal cross-validation?
No, this number is not done in kind of the most ironclad methodological way. This is a single 90-10 random split of this data.
1/10 the size of the data.
It is training on 90% as much data as this and testing on 10%, a random 10% subset.
The testing is the 92.8.
The testing is the 92.8. But it could be that I happened to choose the hardest 10% and it was a bad split. I didn't do cross-validation for this number. This is also, all right, what does it mean to go from 81 to 88? Basically, kind of your subject verbs go away, your modifiers go in the right place. And I would broadly characterize this change as, at this point, there's still some kind of just things that are wrong. You've learned them and they're just not right and they're always wrong and you would always want them to go away. A lot of what's left is the fact that there are ambiguities, and this model is so simple that kind of it has no way of, it's not lexicalized in any way. There's nothing complex. There's no recursive structure. It's just not capable of actually resolving the ambiguities. But what it's done is detected the grammatical structure in a broad sense, which is kind of a different goal. How general is it? So here's English. These are the times where I show you the lowest number and the highest number, so you kind of get the whole contrast and go, wow. This is English. You can do it for German. By the numbers, it works slightly better. This is worse, right? I can only justify that by showing data. This is slightly worse than this. Chinese, it's pretty grim. I will point out that even supervised parsers tend to have double error rate, but this basically, it's not working all that well. Part of that is because of the part of speech choices in the Chinese tree bank. We just use them. The parts of speech are so deficient that there's almost no structure that you can detect with just the parts of speech. But what's interesting is the dependency models are still improving with the combination, and they're not so much worse than the English dependency numbers, even if the constituency numbers are terrible. This is where I promised I'd conclude, so there you go. Basically, the arguments I'd like to make is you can get these unsupervised methods to work, but in order to do that, you have to go through this process of starting with a model, seeing what gets learned, looking at things like my transition structure should have looked like this and instead it looked like this, and then trying to think, what do I need to do to my model to either enrich it or blindfold it in order to get it to do the right thing, because blindfold is wrong. Put blinders on it, and if you kind of constrain and nudge and blind your models enough, this will basically work. These models do learn reasonable things if you understand what's distracting them. I mean, it's kind of, I guess it's like working with a kid, right? You figure out what's distracting it, you kind of get rid of all those things, and when kind of the only thing that's left is the structure you were hoping to learn, then you can start making some progress. So that's it. Thank you so much for being here for like a double talk. I appreciate it, and that's it.
I have a question. The best F measure
Yes.
on parsing is something like 90 point something.
Yes,
right?
on like much longer sentences and
I see.
yeah.
Okay, but what would the F measure be here actually? I mean, I know
oh yeah, okay.
you're just doing a recall.
Yeah, no, I have the F numbers here. I even have them here somewhere. It's like, okay, off the top of my head, 5% worse. I mean, the precision's 10% worse. The precision's always going to be much worse because these are binary structures and the tree bank isn't. So the precision's something like 88. The precision's something like, I think the precision is 10% lower and the recall is 5, but it may be 20 and 10. I can check them for you. Yeah, let me actually look. But yeah, it's not, I mean, it's not, I'm not, to be clear, the reason those are recall only is because it makes it more friendly to non-NLP audiences. These are F1 scores. This is only for the constituent context model. So here, this 71, you can compare that to I was reporting 80 or 81 or something. I don't remember the number, but so it's about 10% lower in F. But the reason I don't like talking about these, aside from, everybody likes to say 80 instead of 70, but you get into this game with having to talk about an upper bound because binary trees can only do so well against the tree bank. But basically, there's a 10% loss. Excuse me? Yeah, it's also worth pointing out that if you want to talk about precision, you get into these hard questions about it's not reasonable at all to think that your model should be able to guess that the tree bank didn't bracket inside noun phrases. I mean, if your model did that, you have to say it's doing something wrong. That's just crazy. Right? It's not the model's job to know what was in the tree bank designers' heads and their policy decisions. So if you want to talk about precision, you need to have some way of dealing with that, and recall avoids that. But it also lets you just put crazy brackets in the middle of your flat verb phrases and not get dinged for it.
One question. Didn't you ask a question?
Yeah, but Sanju said
people are hungry. This is still true.
Okay, I wanted to. I was thinking, in reaction to your comments about PPs attaching to the wrong place, about the old Hindle and Ruth work from like 1993, I guess, where they started. They said, okay, let's take a partial parser, and let's try to learn off the unambiguous attachment cases what the lexical preferences are. So you can imagine that you, sort of extending that into modern terms, you can imagine that you take something like yours and then you do confidence thresholded self-training in order to try to bootstrap a lexicalized model off of this and thereby start getting the some of the more difficult ambiguous attachments right.
Yeah, so I mean, you're going to start forcing me to put in my other hat where I start talking about my supervised opinions about the world. I think in general, even lexicalized parsers now have been shown to not be really driven by these lexical pairs so much, although PP attachment may be a case where really it is. I still think that, you know, the biggest gain is actually learning what the different kinds of prepositions are and what they're for. So prepositions are a mixed bag. And if you just make the distinction of there are 6 kinds of prepositions, and some of them are for modifying verbs and some of them aren't, that alone would be a lot of progress. Now, you know, that has nothing to do with your question. The answer to your question is if you use something kind of like confidence thresholding to start learning better parameters, that may be a way to do what I talked about having models with higher capacity that aren't distracted by them. By learning something in a low capacity model, the trick is knowing which of the things, so you have these full bracketed structures, which of those brackets are brackets that were wrong and now I need to go learn by some other mechanism, and which are ones that were right. That's a hard question, but I mean, I don't actually have an answer, so I certainly can't respond to that with a better idea.
Yeah. In case of unambiguous attachment, because there's only one possible place to attach.
Yeah, I mean, I think something like that would be promising. I don't have, you know, I can't think of anything that will work better for getting lexical probabilities in. I mean, I can tell you stories that would make sense about having. Okay, I'll tell them to you at lunch.